Hi, thank you everyone. Thank you for the kind words, Vinod. So I represent, both me and Patricia represent Kaiser Permanente. We have been working on many aspects, and we're going to talk about one of those aspects here. Before I talk about that, I wanted to talk about Kaiser Permanente a little bit. So Kaiser Permanente is an integrated healthcare organization. It is the largest, in fact, the healthcare. It is larger than 42 states and 148 countries. We have 17,400 physicians, 48,000 nurses, 38 hospitals, about 600 outpatient facilities and medical offices. Our operating revenue is around $56.4 billion. So we are an integrated healthcare system. What that means is everything under one roof. So if you are a patient, you can get everything there. So we don't drive for treatments, but we really focus on the outcomes. Since we focus on the outcomes, and we have 10 million patients or 10 million members, you can imagine the amount of data we have. So we have really the big data that we need. The next thing is technology innovations. Kaiser has been one of the most leading healthcare companies as far as technology goes. As early as the 1960s, Dr. Sidney Garfield and Dr. Maurice Collin, they were talking about using electronic health records, or electronic computers at that point. We were supporting healthcare technology. So we talked about EMR records, which is electronic medical records, in 1974. So we have immense amount of data that can tie these things together. Any guess who this person is? So I guess almost right. Okay, so this is Dr. John Snow. Any talk about data science or using data to save lives is incomplete without talking about him. So he's the first person in recorded history to use data to save lives. Now, Dr. John Snow was a physician, more specifically a OB-GYN. He was very much interested in medical science and how data can help. He had written a paper back in the day in 1847 saying that cholera at that time was due to sewage mixed with water. But the scientists and the medical professionals over there thought that he's wrong. And they said that, okay, we don't believe you. We believe that cholera is caused due to bad air or pollution. So this was in 1847. In 1854, there was cholera. So for those who don't know how is cholera being caused, because it's more or less extinct, it is an intestinal disease. It can be fatal within few hours of the first symptom. So the popular belief, as you can see, was bad air. So Dr. Snow, with all his curiosity, went to the medical hospitals, started collecting data about the patients. And this is back in the day. So he was playing a role of a data scientist at that time. So he was collecting data. He was trying to put together all the information, where these people were born, what is the age group, where they worked, and all the information that he could get. So what he then did is he took a map of Soho. So Soho is an area in London. It's in the city of Westminster. What Dr. Snow did is he started putting together these dark lines. You can see these lines here of all the cases that had cholera. And he had a hypothesis that wherever there is a water source, there is a high probability of having cholera. Because back in the day, in 1800s, there was no running water at homes. So people used the communal wells or pumps to get water. Businesses would basically buy this water from a bottling system that time and use this water. Also, back in the day, the septic system was not that great. Septic was not properly controlled and was properly used. So what Dr. Snow found out that based on his hypothesis, there was one pump, which is out here on the Broad Street, which had maximum number of cases nearby. And then he looked at other areas. So he looked at other areas, other pumps, and there were hardly any cases near these two pumps. So he had a hypothesis that cholera is caused due to water. And so he wanted to test that. The situation was very dire. People would do whatever to stop cholera because it was causing so many lives. It had already costed like 500 lives. So he went to the pump, and can anybody guess how did he stop cholera? Stop the pump? No, that's good. That's one good. No, but he did even easier than that. Why go in stopping the pump? He actually broke the handle. So you see this? There's no handle. So he was smart. So he broke the handle, people and had to go to other pumps to get water, and people saw that within few days, the incidence of cholera started reducing. So that was back in 1854. Now let's fast forward. Let's fast forward 150 years. It's 1900, 1950, 2000, and today, 2015. So today, we have an unprecedented amount of data. This is life in 60 seconds, right? How many tweets, how many messages. On top of this, today everything is interconnected. You talk to physicians, you can call physicians, you can send text messages to physicians. You have everything integrated. Everything that you need is real time now. You can get information real time. Technology has helped us a lot. In fact, technology has helped us to a level that we found water on Mars as well. But we still lose lives, and we can still use data to save lives. We're going to talk about one such use case. Patricia is going to talk about one such problem that Kaiser is trying to solve right now. Patricia.
Thank you, Taposh. So one of the problems that we have, and I'll describe today, is that multiple studies have shown that patients who are sitting in the medical surgical ward unit and suddenly deteriorate and have to be rushed to the ICU experience much worse outcomes than patients who are admitted to the ICU directly, or patients who are transferred to the ICU before they crash. In fact, patients who experience an unplanned transfer to the ICU experience 2 to 5 times the mortality of patients who are directly admitted to the ICU, and they would stay in the hospital on an average of 8 to 12 days more than patients who are directly admitted to the ICU. These patients are a very small percent of all of our admissions in the hospitals, less than 5%, and yet they account for about 1/4 of all of the ICU admissions. They account for 1/5 of all the deaths in the hospital, and about 1/8 of all of the hospital days in the hospital. So these unplanned transfers to the ICU have worse patient outcomes, and we wonder, can we predict, can we find out who are these patients who are likely to crash and be rushed to the ICU, and find who they are ahead of time and do something about it, intervene and avoid these events. Sort of build an early warning system. Systems like we all know exist for preventing or preparing for a fire, for an earthquake, for hurricanes. In fact, it is true that these patients who experience an unplanned transfer to the ICU, they show physiological deterioration between 6 to 24 hours prior to experiencing the ICU transfer. So, and many times, most of the times today, the doctors and the nurses do not see this happening. One reason is because there is a combination of the physiological factors that make this warning. The other is that they're not necessarily with the patient all the time. So we miss this opportunity and we rush the patient to the ICU. So it seems intuitive today with all of the data Taposh described, all the data that we have with the electronic medical record, it seems intuitive that we would be able to measure these physiological deteriorations ahead of time build some kind of mechanism so that we know who are the patients who are likely to experience this deterioration and intervene ahead of time. And in fact, we have. These systems now exist, early warning system that identify patients who are likely to collapse and crash. They exist today. Some of them are built based on expert opinion. For example, I'm listing the Muse, the News, the Views. These systems are all in the UK. The UK has actually implemented a system that warns the clinicians of an impending deterioration of a patient. These were based on expert opinion. And there are systems that are based on a statistical model and a lot of data. One of them is the Rodman Index and the E-card. We at Kaiser Permanente have developed an early warning system that we're calling the Advanced Alert Monitoring System to identify patients who are likely to experience, to crash. And we identify these patients 12 hours before they experience deterioration. And actually, our team is sitting here in the first row. This is the people who developed the system. We all did it together. And as any early warning system, it has 4 components. It has the risk analysis, or the creation of the score, the monitoring and warning component, dissemination and communication of this, the score, and then the intervention. For the risk analysis portion, this is the building of a score that provides the warning. We have used bed history data, meaning where has this patient been in the past few days since the patient was admitted to the hospital, chemistry, so that is all the lab work, all of the vital signs, or any vital sign information. We're collecting vital signs consistently for the patients in the hospital, so that's readily available to us. Any comorbidities, because as Taposh described, we and our organization take care of the patient from the clinic to all the way to the SNF. We have information on these patients, and we know about their comorbidities, so we can bring in all of their past behind into our models, and demographic information, so age, gender, et cetera. And we've used all of this information to estimate either the probability of a late transfer into the ICU, that is a sudden crash, or mortality in the hospital. And this AAM, the Advanced Alert Monitoring System, is calculated and can be calculated every hour. Right now, it's being calculated every 6 hours. And it's available now. And what happens is that our clinicians get this monitoring and warning. When a patient is about to crash, there is a warning that comes up in the screen for the patient's data. So there's a pop-up alert that displays if the AAM exceeded the threshold that we've identified as the threshold for action. And what happens is that once that threshold is exceeded, then the team comes and evaluates the patient, and a decision is made as to what needs to happen to that patient. Ideally, where does this go? Oh, here. So if in this picture, if there's no intervention with the AAM triggers, then the expectation is that the patient will experience worse outcomes. But if we are able to intervene at this point prior to deterioration, then the team can either send the patient to the ICU earlier and not in an emergency basis, or provide any intervention that's appropriate at this point and avoid the transfer, but definitely avoid the worst outcomes. So Taposh will continue with the.
Thank you, Patricia. So in the next few slides, what I'm going to talk about is using data science to save lives in a way which is more realistic to a data scientist. So we'll go through the development process that happens in our organization. We go through all the processes that we do to make a model to production. We'll also talk about the challenges that we find, and we'll take it from there. So the development of the risk model process is like any other data science process. I joined Kaiser from advertising ad tech. So the process and the pipeline for a development is pretty much the same. We get relevant data. That's the most important thing. We spend a lot of time getting relevant data. We have a data pipeline, and then we do a refinement of the data. The reason we do a data pipeline because you can repeat the refinement process. If you have multiple models, you have multiple pipelines. We clean it, impute it, and then we go to the feature engineering aspect of it. We do feature engineering depending on what tools are supervised or unsupervised learning that you are using. You will have the depth of feature engineering there. And then we apply a variety of training and testing data sets. So this is pretty much similar to what you would do on a Kaggle data set. The difference is we have a dashboard for model performance. The part where we are different is the validation of the models. Now, if you were doing Kaggle, you would have a validation data set where you could easily validate. But when you're talking about saving lives, you cannot be off by even a bit. So we do a very rigorous process in validation. We go through parameter exploration, where we explore each and every parameter and its linkage. We get the clinicians involved. They look at it at each and every case. They look at it. They look at the research material. They see it makes sense. Then we do a characteristics review and a threshold analysis. So we understand what threshold makes sense to call it if it's a classification system from 1 to 0. Productionalizing the model. Healthcare is a highly regulated industry, and displaying new patient information is always complicated, challenging. We have to go through a change management process because if you're talking about ER rooms, it's a high pressure area, so you have to do a good change management to get anything in place there. The next part is the POC aspect of it. So we did proof of concepts, actually several proof of concepts to improve the infrastructure, the processing time, recent machine learning algorithms, ensembles of recent machine learning algorithms, big data tools available to us. And we learned a lot, actually. We saw how faster processing can help. We saw how faster access to data can help. We decided that we will no longer sample data because we don't need to sample data with this new advancing tools. We found out how it was easier to add new features. And finally, but we decided open source was one of the right ways to go, as long as you have support. The use case that Patricia talked about had a couple of challenges. The overall event rate was very low, which is good in a way because you don't want unplanned transfers to be high. You want it to be low. But that makes it difficult when you are doing any analysis of it. Then we were trying to look at the event rate within a narrow 12-hour period because our data needed that. So that was extremely low. So we had to get longer data for a longer period of time. So other thing was the extreme care and highly involved validation process. And finally, this was a class imbalance problem for us. So we, in addition to the traditional methodology of using ROC curve, AUC, sensitivity, specificity, we started looking at other cost curves, PR, precision recall curves to compare a variety of algorithms. Next steps. So we believe that continuous testing, continuously improving, doing A/B or multi-arm bandit testing will really help us. We started looking into new features to be adding to the training model. We started enriching our model, and we'll keep on doing that. We compare all the models with a matrix set of things, which includes PR, cost curves, and everything else. And we keep on improving the monitoring and the warning process. So this is Jeff Hammerbacher. He is the co-founder of Cloudera. He once said, the best minds of our generation are thinking how to make people clicks. And I really used to think that he's right, 100%, because that really stinks, because all the talent is just making people click ads. Then this is by my manager. The best minds of my generation are using data to save lives, and that rocks. Finally, I would like to acknowledge the entire team. Part of the team is here, who made sure that we could do this. It almost takes a village to get anything done. So the data pipeline, everything from an IT engineer to a statistician, everybody was involved in this process, in this project. And I'll end with saying that healthcare needs you. So we are hiring. We're looking for more data scientists to join us. Thank you. Thank you for the time.
So I actually have a question.
Oh.
Before I hand over the mic. For your healthcare example where you're looking at AAM data, can you talk about what sort of benchmarks you used or cost functions to evaluate when to intervene given a signal?
Benchmarks, when to intervene different signals. Patricia, can you help us?
So at this point, this engine, the score, is being piloted, and the way we're piloting is mostly on resources. So we have agreed with our physicians and nurses that we cannot have more than a certain number of alarms per day, because the process is just being piloted at this point. But as we see how it works and see the interventions, how successful they are, then we will expand to more resources. So that's basically how it was done.
Thank you.
How do you rate the physicians? Like, do you have any science behind to rate the physicians? Like, okay, he's good in this or like.
So the question is, how do you rate the physicians?
Yeah.
So we are not, the use case is not about rating physicians right now. I mean, this is not about rating. So we are trying to create something to solve unplanned transfers.
The reason I'm asking, like, we generally prefer to, hey, this physician is good. We'll prefer that the star, 5-star, like that. So you have any logic behind that in the hospital? If I go to.
No, I don't think we have any logic on rating physicians. Good question.
We have time for 2 more questions.
Yeah. I think there's one here, yeah.
How do you handle the false positives?
How do I handle
The false positives if the signal triggers some false alarm or make some wrong predictions?
So we, as I was explaining you, that we go through a very, very, very rigorous process. Given that, yeah, false positives do occur, and we have to handle that. So we do a very rigorous process to understand that that it's not a false positive. So we look at sensitivity, specificity, scores that highlight those things as well. So reducing them or looking at the type of the score and working on them is what we look at. So validation is a very, very important thing for us. We take it very seriously. So that's one of the things, because if I'm doing an ad tech and if I click an ad by an accident or I make somebody click an ad by accident, it's okay. But when you're talking about medicine and saving lives, it's a very, very different area to think into.
Yeah, I mean, actually, with the false positives, what we're hearing from the field is that the patients that are being identified, it's not a problem about, oh, this is the wrong patient. Mostly it is the right patient, but mostly they already knew about the patient, so, okay, this makes sense. So that's been more of the problem. The other problem with this particular use case is that as you intervene, you are avoiding the outcome that you're trying to predict. So as we are going to be piloting this score in more and more of our facilities, what's going to happen is that we are going to have to be changing the model because we are tracing towards an outcome that is hopefully not going to occur. So that's a challenge in terms of evaluating how good our model is, because our outcome is kind of slipping by.
Yes.
So somewhere in your process, you mentioned that you take feedback from the physician. When you talk to 2 different physicians, they sometimes have different views on how serious a patient is or what the next action should be taken. How do you incorporate the physician's feedback into your mechanism? And do you also look at prior cases where you really made some mistake or how you can improve the model?
So we have a lead physician who's leading the clinical portion of this project. And he has developed the protocol for what to do with the patients when the alarm sounds. But of course, there is also the particular physician who is a treating physician at the point of care. However, we would take feedback from the various physicians, and the lead clinician who's leading the intervention will incorporate or not into the protocol.
So yeah, we take input from a lot of physicians as well. And these are use cases reviews, basically, to see for this particular case what the value is. And then we take the decision on a data-driven way. Hope that answers your question.
And that's all the time we have for. Thank you.
Thank you.
Thank you.